Hello to everyone who at this hour decided to join our webinar from the Young Members Group of International. The past year was full of hot topics. Dozens of questions were answered. Each of us, I think, each of us learned something new or unusual about this wonderful world of the most popular building material, which we call concrete. The last year of our webinars was mostly dedicated to research and scientific topics. But this year we decided to make directions of our webinars and other activities toward the practice. I'm sure that you have attended our past webinars in January and February. If not, you can always view all of our webinars on the official FIB YouTube channel. Today's topics you can see on your screens, I think can be equally attributed to both to theory and to practice. And for my opinion, it stands apart from the rest of topics that we heard. Today we will discuss with you the problems of fire resistance of concrete structure. Leading this webinar will be by me. My name is Oleg. I am from Ukraine. I'm a chair of Young Members Group in Ukraine and board members of Young Members Group International. First of all, before we start, I must tell you some general information about our webinar. So the webinar will be recorded and shared on FIB social channels. Only the panelists are able to speak during the webinar, but you can use chat function where you can post where do you come from and general feedbacks, but not the questions because we have special forms for them about the webinars. Any opinion, we will read it. Absolutely, and have reaction on your trying to answer you. But you have on the bottom of the screen the Q&A forum where you can post questions for the speakers, and we will answer to all of them at the end of the webinar. So please use the Q&A forum if you want to ask questions, and we will surely answer it after the presentation. The next that you must know that the participation in the webinar is completely free of charge. But also by the popular demand, we have the opportunity to provide you with a certificate of participation of the webinar. And if you need a certificate of attendance, you should contact, you see the email here, publication8@fibinternational.org, and to ask your wish about this certificate. The certificate has fee. It will be 10 Swiss franc. But only people who attend at least 60% of time of this webinar can request such certificates. So before I officially introduce today's speaker, and we will start our evening webinar, I will tell you something about our Young Member Group activities. So what are we doing? The main thing, the main goal, the main idea is that the FIB Young Members Group represents a platform for dialogue between young professionals. Also, we encourage the creation of National Young Members Group, if you haven't such in your country, involving young people in FIB commissions and task groups, making and maintaining contacts and networking, organizing regular meetings, many events and conferences for young members and young engineers, organized the best paper award competition during the FAB symposium, and many more interesting things which inspired by our professional hobby and concrete. So also, if you want to be a part of our community, feel free to contact us in any way suitable for you. We also maintain our Facebook page. So subscribe, like, and you can also visit our section on the official website where you can find all the information about our activities, about our group, and information how to become a member, how to join us. So please don't hesitate to connect us. Okay. So finally, we smoothly moved on to the things that united us on this spring evening. So who is our speaker? Let me introduce Oleg Fesenko. His master degree, he got master degree from Kyiv National University of Construction and Architecture, Ukraine. His PhD thesis topic was progressive collapse of multi-story reinforced concrete buildings due to fire following earthquakes, with Professor Nemchinov at the State Research Institute of Building Construction in Kyiv. This is the main research institute of constructions in Ukraine. He spent 16 years in practice at the State Research Institute of Building Constructions from 2005 until today. His main focus of his occupation is structural fire design. He's also head of the sector for fire resistance of building structures in Research Institute in Kyiv. His FAB involvement, he's coordinator from national group in FAB Young Members Group Ukraine. He's involved in the work of FAB Task Group 2.3, fire design of concrete structures and post-fire assessment. So I hope that I intrigued you and you are waiting with patience for to start our webinar. Now I could finish my speech and give control to my colleague, to my good friend Oleg Fesenko. So Oleg, now I give you control. You now king of the show. So please do share your screen, and we all waiting for your speech.
Hello, colleagues, all participants of this webinar. Thanks, Vlad, for my presentation. And let's talk about the topic. First of all, I want to thanks everybody for your time and attention. Today, I want to introduce my favorite topic about fire resistance of concrete structures. My report is mainly based on part 1.2 of Eurocode 2, FIB bulletins number 38 and 46 about the fire design of concrete structures, and mine of my colleagues, researchers. Aims of our today's report are to set requirements, to apply actions on structures exposed to fire, to describe properties of concrete and reinforcement steel at elevated temperatures, to determine design procedures, to introduce tabulated data, to present results of numerical simulations. About the fire resistance, the definition is ability of structure or part of structure or member to fulfill its required functions, load bearing function and or fire separating function for a specified load level, for a specified fire exposure, and for a specified period of time. EN 1992 Eurocode Part 2 Eurocode 2 Design of Concrete Structures General Rules Structural Fire Design. Let's talk about requirements. The following essential requirements for the limitation of fire risk is the construction works must be designed and built in such a way that in the event of an outbreak of fire, the load-bearing resistance of the construction can be assumed for a specified period of time. The generation and spread of fire and smoke within the works are limited. The spread of fire to neighboring construction works is limited. The occupants can leave the works or can be rescued by the other means. The safety of rescue teams is taken into consideration. And the main design requirements as for load bearing and separating construction are to maintain load bearing function during the required time of fire exposure when mechanical resistance in case of fire is required, and to maintain separating function during the required time of fire exposure when compartmentation is required. There are fire resistance criteria. Three main criteria are defined in Eurocode. For standard fire exposure, structural members shall comply with criteria R, E, and I as follows. Load bearing only, mechanical resistance. As you can see, it's a criteria R. When you need to separate separating and load bearing criteria R, E, and when requested I, and separation only integrity criterion E, and when requested insulation criterion I. Actions and need to tell about this criteria more detailedly. Criterion R is assumed to be satisfied when load bearing function is maintained during the time of fire exposure. Criterion I may be assumed to be satisfied when the average temperature rise over the wall of the non-exposed surface is limited to 140 Kelvin and the maximum temperature rise at any point of that surface does not exceed 180 Kelvin. And let's talk about actions. There are two kinds of actions on structures exposed to fire, mechanical and thermal actions. Structural fire design analysis takes into account the following steps as relevant. Selection of the relevant design fire scenarios, determination of the corresponding design fires, calculation of temperature evaluation within the structural members, and the calculation of the mechanical behavior of the structure exposed to fire. Thermal actions for temperature analysis. Thermal actions are given by the net heat flux to the surface of the member. One of the fire exposed surfaces, the net heat flux should be determined by considering heat transfer by convection and radiation. The standard temperature time curve is given by the equation on this slide, and also can be described on standard temperature time curve. About the mechanical actions for structural analysis. For an assessment of indirect actions, the following should be considered. Constrained thermal expansion of the members themselves, e.g. columns in multi-story frame structures with stiff walls, different thermal expansion within statically indeterminate members, e.g. continuous floor slabs, thermal gradients within cross sections given internal stresses, thermal expansion of adjacent members, e.g. displacement of a column head due to the expanding floor slab, thermal expansion of members affecting other members outside the fire compartment. Another part of structural fire design is material properties of concrete and reinforced steel. Let's talk about the properties of concrete. It can be described this curve, and also the values of material properties shall be treated as characteristic values. The strength and deformation properties of uniaxially stressed concrete at elevated temperature shall be obtained from the stress-strain relationships as presented in this figure and the next one. Curves for different temperatures from 20 to 1000 degrees. The stress-strain relationships given in the figure are defined by two main parameters: the compressive strength and the strain corresponding to this strength. As you can see, ultimate strain and the strain corresponding to compressive strength of concrete. As you can see also on these curves, ultimate strains more for different different temperatures. Also, material properties of reinforced steel can be described by this curve. The strengths and deformation properties of reinforced steel at elevated temperatures shall be obtained from the stress-strain relationships specified in this figure. The stress-strain relationship are defined by three main parameters: the slope of linear elastic range, the proportional limit FSP, and the maximum stress level, and also ultimate strain for reinforced steel. Design values of mechanical properties can be defined by the equation, where you can see xk is the characteristic value of the strength or deformation property. For example, compressive strength or model of elasticity of concrete. K is the reduction factor for a strength or deformation property dependent on the material temperature. And the partial safety factor for the relevant material property for the fire situation with index Fi. Another kind of properties of concrete are thermal properties. There are thermal conductivity of concrete and specific heat of concrete. For the thermal conductivity, we can say about lower and upper limits of this range of thermal conductivity. The lower limit of thermal conductivity has been derived from comparison with temperatures measured in fire test of different types of concrete structure. The lower limit gives more realistic temperatures for concrete structures than the upper limit, which has been derived from tests for steel concrete composite structures. As for specific heat, we can see the value of moisture content of concrete and the influence of this moisture content, which describes the peaks on this curve. Where moisture content is not considered explicitly in the calculation method, the function given for the specific heat of concrete may be modulated by a constant value situated between 100 and 115 degrees, with linear decrease between 115 and 200 degrees. As you can see, peak values of specific heat depends of moisture content of concrete. The peaks of specific heat for moisture content of 0, 1.5, and 3% of concrete weight are illustrated on this figure. Design values for thermal properties. Design values for thermal properties can be defined for two cases. If an increase of property is favorable for safety, it's equation 1, and if an increase of property is unfavorable for safety, equation 2. X is a characteristic value of thermal property for normal temperature design, and the partial safety factor for the thermal property for the fire situation. Now we can talk about the design procedures. A full analytical procedure for structural fire design would take into account the behavior of structural system at elevated temperatures, the potential heat exposure, and the beneficial effect of active and passive fire protection systems, together with the uncertainties associated with these three features and the importance of the structure consequences of failure. The following design methods are permitted in order to satisfy detailing according to recognized design solutions, called tabulated data, or testing, fire testing. Simplified calculation methods for specific types of members. Advanced calculation methods for simulating the behavior of structural members, parts of the structures, or the entire structures. One of these procedures, most conservative of these three described above procedures, is tabulated data. The tables of standard fire resistance have been developed on an empirical basis confirmed by experience and theoretical evaluation of tests. The data is derived from the approximated conservative assumptions for the more common structural elements and is valid for the whole range of thermal conductivity as lower and upper limits. Tabulated data gives recognized design solutions for the standard fire exposure up to 240 minutes. As you can see, this is a tabulated data for RC columns. In this table, standard fire resistance of columns depends on such factors: cross-sectional dimensions, minimum of these dimensions, weight or height, also axis distance of the reinforcement bars of the columns, number sites of fire exposure, 1, 2, 3, or 4 sites or more than 4, and a degree of utilization or load level in the fire situation of column. There are different data for each range of fire resistance. You can choose minimum values to satisfy standard fire resistance. There are tabulated data for RC flat slabs. It also depends on some parameters. It's slab thickness and also axis distance to reinforcement bars. You can see range of fire resistance from 30 minutes to 240 minutes. As also you can see, for the column, the main criterion is R, load bearing capacity, as you can see in the first column, and the number is the period of time. And for the flat slabs, which have to satisfy compartmentation, there are 3 criteria: R, E, and I, and also period of time. And in complex, it gives you fire resistance class R, E, I, and 40, for example, 45, 90, 120, and so on. As for tabulated data for reinforced concrete beams, for example, simply supported beams with reinforced and prestressed concrete, you also can see the criterion R and a period of time. The main criteria for beams is R, because beams are only load-bearing elements. And also you can see the parameters on which depends the fire resistance. They are minimum dimensions of the cross section. For example, it's the weight of cross section of beam, and also the axis distance for the reinforcement bars. If you want to assume the resistance with using this tabulated data, you have to choose your standard fire resistance, what you need to satisfy, and you have to find the combination of minimal dimension and the minimal actual axis distance for this standard fire resistance. Okay. Another kind of design methods are simplified calculation methods. Simplified cross-sectional calculation methods may be used to determine the ultimate load-bearing capacity of a heated cross-section and to compare the capacity with the relevant combination of actions for the fire situation. Simplified methods for the design of beams and slabs where the loading is predominantly uniformly distributed and where the design of normal temperature is based on linear analysis also may be used. One of the example of this simplified method is zone method, which require the reduction of strengths and cross section for the sections exposed to fire. This method of subdividing the cross section into several zones is described on this slide, on these figures, for different types of structures: walls, slabs, beams, columns, and for different numbers of sites exposed to fire. For example, beams are exposed on 3 sides, and slabs are exposed only on 1 side, and columns can be exposed till 1 to 4 sides. The cross section is divided into a number more than 3 numbers of parallel zones of equal thickness, where the mean temperature of corresponding and the corresponding mean compressive strengths and modulus of elasticity of each zone is assessed. The fire damaged cross section is represented by reduced cross section, ignoring a damaged zone of thickness and the fire exposed at the fire exposed sites. When the reduced cross section is found and the strengths and modulus of elasticity are determined for the fire situation, the fire design follows the normal temperature design procedure similar to that shown on this slide. This is a scheme of stress distribution at ultimate limit state for rectangular concrete cross section with compression reinforcement, and it's a reduced cross section of the beam, for example, and also we use the reduced strength of reinforcement, which on the side exposed to fire, and we also use the normal strength, compressive strength of the concrete in the compressive zone. As you can see, it's a scheme of design reduced cross section at the normal temperature design procedure. And the highest level of calculation methods are the advanced calculation methods. These type of methods shall provide a realistic analysis of structures exposed to fire. They shall be based on fundamental physical behavior leading to reliable approximation of the expected behavior of the relevant structural component under fire conditions. Any potential failure mode not covered by the advanced calculation method shall be excluded by appropriate means. For example, insufficient rotational capacity, spalling of concrete, local buckling of compressed reinforcement, shear and bond failure, damage to anchorage devices. These advanced methods should include calculation models for the determination of the development and distribution of the temperature with structural members, thermal response model, and also the mechanical behavior of structure or of any part of it, mechanical response model. Two parts of this kind of design, thermal and mechanical. Let's talk about thermal response. The main principles of this kind of calculation are the advanced calculation methods for thermal response shall be based on the acknowledged principles and assumptions of the theory of heat transfer. The thermal response model shall include the consideration of the relevant thermal actions specified in European norms 1991, part 1.1.2, the temperature-dependent thermal properties of the materials, which were described above previously, and the temperature profile in reinforced concrete elements may be assumed omitting the presence of reinforcement. Another part of advanced calculation methods is mechanical response. It also have some principles. They are advanced calculation method for mechanical response shall based on the acknowledged principles and assumptions of the theory of structural mechanics, taking into account the changes of mechanical properties with temperature. The effects of thermally induced strains and stresses, both due to temperature rise and due to temperature differentials, shall be considered. The deformation at ultimate limit state implied by the calculation methods shall be limited as necessary to ensure the compatibility is maintained between all parts of the structure. Where relevant, the mechanical response of the model shall also take into account of geometrical non-linear effects. And after this theoretical part, now we can talk about practical cases, practical realization of design principles and methods described above. On these figures on this slide, you can see the results of numerical simulation of reinforced concrete ventilation blocks. You can see the geometry of blocks, finite element model, and the results of heat transfer analysis. We analyze three cases: one side exposure, two side exposure, and four side exposure, fire exposure of these blocks. And we have results for different periods of time, for 30 minutes, for 45 minutes, for 60 minutes, and for 180 minutes. As you can see, the results of thermal temperature distribution in the cross-sectional of these blocks. These results were analyzed. This analysis was made by the ANSYS mechanical and ANSYS workbench educational academic set, and the version of 2019, 2020, and 2021 versions. Another case, it's analysis of reinforced concrete stairs. You also can see the geometry, finite element methods, the element mesh, and you can see the thermal distribution on the elements of these stairs. This design, this calculation was made for the period of time 60 minutes, and fire exposure on three sides of this part of stair. This is a result of analytical simulation of the columns with dimension of the cross section 30 millimeters, and comparison with temperature profiles given in Eurocode 2 for this kind of section. As you can see, this simulation was made for different periods, for 30 60, 90, and 120 minutes. This calculation was made in our Ukrainian finite element complex called Lira SAPR, SAPR. And another type of temperature profiles for reinforced concrete columns with different cross-section sizes. This size are different from that profile temperature profiles given in the Eurocode. This cross-section size are more typical for the main types of columns in building practice. The dimension of this rectangular cross-section are 400 millimeters and also 500 millimeters, and the periods of time are 120, 150, and 180 minutes for the criterion R for the load bearing capacity. Another kind of analysis was made for the reinforced panel panel wall subjected to seismic loading. You can see the results of fire test of this wall panel, deflecting mode, and also you can see the results of moisture content in this concrete of this wall panel on the side, on the unexposed side of this wall panel. During the test were determined and measured the temperature on the reinforcement near the exposed surface of this panel. As you can see, the maximum value near the 400s at the period of time 2 hours or 120 minutes. Also, we have temperature across the section, wall panel section, from the exposed maximum value to unexposed minimum value. Also, curves of deflections, displacements of this panel, and we have a comparison of the results of experimental measuring the temperature and calculated with ANSYS mechanical temperature across the section. After this fire test, we also had a numerical simulation of the model of this panel, and we had a deformed shape of the panel and deflections. And finally, we can talk about the case studies, real case studies of collapses due to fire. Some kind of this you can see earlier. As you can see, these concrete structures exposed to fire, different kind. For example, slabs, columns, and different type of collapses, which depends on the fire regime, duration of fire, fire resistance, which normative fire resistance of these structures. This case more realistic because they happened with realistic fire exposure mode, not standard fire, which in calculation. And now I finished. Thanks for your attention.
Okay, Oleg, thank you. That at last we have an opportunity that you share your experience, share your some research practice, tell us about some theory, and we have some questions, and I try to ask you these questions. Maybe you can stay to sharing your screen if you need to show some slide. So don't stop to share it.
Okay.
So about the questions, the first one: is there any relation between density of concrete and fire resistant? Do you understand?
Yes. Density of concrete influence on the fire resistance, but this type of influence not so big that, for example, thermal conductivity or the specific heat or the strength, compressive strength. But yes, density influence is depends of the moisture content, and also yes, it depends, but not so big this influence.
Okay, we understand. We have greetings to you and thanks in the chat for your presentation, for your good work. And another questions. How to handle the pore water, moisture, pressure in the pores when the concrete is subjected to elevated temperature? Firstly, with partially saturated pore pressure, and secondly, with the completely saturated pore pressure. If you don't understand, you can use Q&A actions in your screen and to see.
Yes, I can see this question. What I can say, the pore pressure also influence on the fire resistance more the density, for example, because after the pore pressure we can have spalling of concrete, and we can have the direct exposure, fire exposure on the reinforcement steel. But as for moisture pressure in the pores, unfortunately, I can say about this because I am not so big expert in this type. And good questions and the perspective for our research, future research. Thank you for these questions.
Okay, I also think that is interesting question about pore pressure. It's especially
it's like indirect action, indirect value, which increase which decrease the fire resistance, which reduce the cross section with spelling. And yes, influence is I think big, but I'm not so expert in these questions. Thank you.
Okay, especially about high performance concrete with the pore pressure is an actual thing. Another questions Balaji. Tell me some insight about isotherm 500 method. I think it's Eurocode methods.
Yes, it's one of the simplified method. I told you about the zone method. It's maybe higher level of this kind of 500 method. Isotherm 500 method, but is this method the aim of this method is to determine the temperature 500 degrees in the cross section and reduce this cross section on the size which not in this isotherm, which on the sides of this isotherm. Maybe yes, it's a simplified Eurocode method.
Okay. If you need more accurate Oleg's answer, you can write type in the Q&A sections to ask him more wide answer if you need. Okay, the next questions is continue about density by Suresh Babu. He's thanking for your answer, but saying that per my knowledge, the density of concrete increase does not gives high strength of concrete. Would you mind, can you elaborate relation between strength, density, and fire strength? I think he asked only about the density and about strength of concrete, compressive strength of concrete with fire resistant, and the density. He means, I think, light concrete or normal concrete.
I can show the curve of the density in Eurocode, but about the relation between strength and density, I can talk because didn't see this kind of relations, and it will be interesting to see these results. Maybe we can change or something with these results. And also I can maybe demonstrate the curve of the Eurocode. We have the equations about the variation of density with temperature is influenced by water laws, but I can show you, I can't show you the relations between strength and density, unfortunately. And it will be interesting. It will be interesting to have these relations, to have these results. Thank you.
Okay, let's go forward to the next questions. I think this is the last one from the Q&A section, but I have some of my questions. Was there any different tests for different mesh size in the finite element calculations?
Yes, this test, this type of tests were done, and the calculation results of the maybe more optimized, most optimized mesh of this these structures, but as you know, educational or academical version of the ANSYS is limited for the number of the elements or for the size of mesh, and we are limited in this limitations of the program complex. And yes, we try to do these tests, but now I can't show you the results of this comparison tests. But yes, it influence, and this influence is big.
Okay, I understand about your limitation, but how do you think what is the optimal size of mesh for analysis of fire resistance? How do you think? Because for design calculations, we know that it is like 0.5 meters for slabs, for example. And for your calculations, what is optimal size of the mesh?
As for our experience, there are different kind of meshes for different type of calculations, for different type of analysis. For example, if you need to calculate the temperature thermal distribution in the section in construction, you have to you can do steady state analysis or transient thermal analysis. For example, our calculations were made as transient thermal, and this mesh is one, and the different kind of mesh can be used in steady state analysis. And I can say that it depends of kind of analysis, steady state or transient thermal, and the type of mesh depends of the kind of analysis. But I can recommend it's individual. I can say that it's individual for the different kinds of analysis.
Okay. Yes. Another questions we have one more question. How can we deal with the spelling risk on concrete structures subjected to high thermal stresses? Did you make some experiments about that phenomena? Several parameters can influence spelling. It is very difficult to consider spelling in numerical simulation by FIM. Spelling, do you know what it means?
Yes, spelling, it's accidental cracking and
Yes.
like collapsing failure of the concrete on the sides of exposed sides of the section of the construction. Yes, it's a big problem, as Eurocode recommends to use the reinforcement with small sizes and small diameters of the bars. This mesh, like reinforcement mesh, reinforcing of this cover, concrete cover with mesh, but as we can say about the spelling in numerical simulation, it's I agree, it's very difficult because spelling also depends on the kind of the firefighting. When we use when the firefighters rescue teams use the water, for example, it's essential cooling of this concrete cover, and it's spelling which I think we can't modulate this process of the cooling size of the residential cooling size of with water of the by the rescue teams, maybe but recommendation of Eurocode is to reinforce the cover layer of the concrete of structure of construction. Thank you for interesting question.
Okay, thank you, Oleg. The next questions from another question, I would say for Suresh Babu. What if buried aggregate, coefficient of expansion is placed in concrete? It gives more density to concrete against radiation shielding. Can we suggest the buried concrete for nuclear power plants?
Buried aggregate coefficient of expansion is placed in.
I think he talking about density again. I think the buried aggregate is increasing the density of concrete, and it is a continuing the discussion about density versus fire resistance. I think so.
Buried aggregate for concrete, maybe it's yes, maybe it's a good idea for nuclear power plants, but as we can say about our structural fire design for typical structures with siliceous and calcium aggregates, and also different fire regimes of fire exposure, for example standard fire, and maybe I don't know what kind of fire regime we have to use when we analysis of nuclear power plants constructions, what kind of heating, what kind of cooling, stage heating, cooling, and unfortunately I have no experience with this composite. Maybe yes, but I see some differences with these kinds of structures, and the differences with the kind of fire regimes.
It needs more some researchers in this field. I think so. Some experiments, yeah.
Yes, it will be better to have some tests, some experimental with this kind of aggregate, and to
because it is
to research
another,
this influence.
it is another type of concrete, I think so, with its own properties, which must be studied and using.
Maybe problems of spelling for this kind of aggregate. I don't know if it expansion is more maybe different concrete covers for the reinforcement. Maybe this kind of structures are massive, big thickness, big sizes as for nuclear structures. Maybe different temperature gradients, different distributions. I think it's different maybe from this kind of calculations which were presented by me today, but it's very interesting
Field of research, yeah.
Yes, very interesting questions and very interesting field.
Okay, we have some questions. Another question from Balaji. How can coupled FEM analysis through console software can be addressed multi-failure analysis, such as structural and thermal failure of the structural elements under elevated temperature?
Unfortunately, I have no experience with the console software. I heard about this, and it's great. It's good software, but not so expert in this kind of analysis and in this software, and maybe can't answer these questions.
Maybe if he has some results and or some articles or some publication about his experience in such software, he could mail you. I have posted your email in the chat. So if you want to share your experience, you can share it with Oleg by mail.
Yes, COMSOL is also multi-physical, multifunctional software, but I'm not ready to answer this question.
Okay, I understand. We have another question in the chat from Marta. We are happy that you're here, and thank you for your support. The question is, thanks Oleg, how the effect of a preceding earthquake can affect the fire resistance of structure leading to progressive collapse? This question is in the chat if you want to read it.
Yes, thank you. It's about my topic of my thesis, which called by Vlad in the beginning. In that research, we try to research the influence of post earthquake fires and the influence of this kind of fires influence on structures, on concrete structures, and what kind of this influence as you know, maybe from the history, there are many kind of earthquakes, great earthquakes. Also can be followed by fires in in the residential houses and fires maybe different kind of fires like San Francisco earthquake in 1908, big fire, and maybe earthquake in Tokyo in 1930 or 1923. And following the earthquake, fires can I can see another kind. The fire is a stimul of the earthquake is a stimul to begin the fire, and rescue teams in these situations have two two different problems with the earthquake collapses and the fire spreading between the houses, between the blocks of the city, and also the influence is the damages which conducted, which were earthquake or seismical damages reduced the fire resistance, reduced the cross-sectional dimensions, and reduces the fire resistance. As with the different kind of failure, cracks and like maybe also spelling and different type of collapses and failures reduces the potential fire resistance of the constructions.
Okay.
And also can be issue of the progressive collapse in the future as a stimul, as a progressive collapse as a result of seismical action and fire and the fire following earthquake.
Okay. We have ended the questions from our participant, but I still have my questions. So if you don't mind, I will ask you. My question is about results of your numerical analysis. On these results, no results were seen in the reinforced concrete columns or concrete columns about the temperature. The digits was too low, so I ask you to say me what is the temperature inside the sections at the places where the reinforcement is usually located. I don't clearly understand if you have calculations about reinforced or only concrete element. But it is interesting what is the temperature in the places where we situated the reinforcement. How many degrees?
Yes, good question. Thank you. I can answer you, but it's about thermal response. One of the the point 3, the temperature profile in reinforced concrete elements may be assumed omitting the presence of reinforcement. We can, I can say, ignore or reinforcement, or we can say the temperature in the in the concrete cross section, in this point where reinforcement bar situated is the same when is the same as the temperature in this reinforced bar. We have this assumption, the temperature profile.
Okay, I understand this theory, but what is the temperature? Can you say the value of the temperature? For example, 40 millimeters from the face of the column. What is the temperature on this layer? It is interesting. What temperature will be on the reinforced bars?
First
The
of all,
the value of the temperature. How many degrees is?
First of all, the temperature depends on the on the axis distance, for example, 40 millimeters, and also it depends of time of exposure of the standard fire resistance. For example, it's 30 minutes or 1 hour or 2 hour. And the temperature will be different. And we can.
Do you have this? Sorry, Oleg. Do you have this value on your slides when you show the cross section of columns for 400 on 600? It is interesting to know the value.
We can assume by these profiles, maybe for this kind of.
This or next slide.
Yes. For example, if you're talking about the 30 minutes or 1 hour or 1 hour, for example, if you're talking about 40 millimeters and the size of the rectangular cross section 300 millimeters, and as you see, it's near the 500 degrees is in the after the hour of the fire exposure. After the 1 hour of fire exposure, we can assume the 500 degrees in the reinforcement situated on the axis distance 40 millimeters.
And the reinforcement could start to leak for such temperature.
Yes, if we use the isotherm 500 degrees method, we can assume this reinforcement like maybe we can neglected this. We can talk about the maybe zero strengths, for example.
Okay, understand. And what about 30 minutes? And 60 minutes we have 500 degrees. And what about 30 minutes? How many degrees we have? Air 30. Yeah. This we have.
It's near it's between 200 and closer to.
It seems to be it is suitable for concrete construction for 30 minutes to evacuate people, and then we have the process, the negative process in the concrete structure. I think so.
It depends. The time of evacuation also depends
30
of
minutes,
of the type of building, and also standard fire resistance for the columns higher than for the slabs, for example, or beams. It's typically for Ukrainian norms. It's typically 2.5 and 3 hours. This thermal distributions, and it's was interesting because this was a typical cross section sizes, and the most valuable period of times for the multi-story frame buildings. This period of times 2.5 and 3 hours, and also we can go back to the tabulated data, and if you want to design fire resisted column or another construction, you have to use this data. They are conservative, but it's very reliable, and as you can see, to satisfy to our resistance for the highest level of loading, you have to design your column with the size minimum of 100.5 millimeters, 150 millimeters, with the axis distance 51.
51 millimeter.
Yes.
Oh, it is.
Axis distance.
Yeah.
And also you need to have minimum 8 bars.
8 bars.
And if you want to satisfy your fire resistance, the simplest method is to use this tabulated data. I can say. For the designers, for the civil engineers, it's very good instrument.
And easy, good and easy. Yeah.
Good and easy and understandable, and it gives it was given in the Eurocode.
Okay. So it was my last questions. I checked the Q&A sections. We have answered all the questions. The chat is full of thanking you for the presentation. If you remember, I told you that we will have a hot discussion after your presentation, because it is not so spread topic and specific direction of concrete designing. And it is interesting for attendance, and you see the discussion, interesting questions, and maybe I share with you your mail again to if anyone want to ask you anything again, that please don't hesitate to contact Oleg. I don't know how to copy your email, but another way, maybe you want to say something, Oleg, your inspiration or feelings after your webinar. Maybe some words to the attendance.
Thank you everybody for your time, for your attention, for your questions. Very interesting questions. Like for me, there are maybe the directions of our future researches, and also it was, as for me, it was a great experience to communicate with FIB, to communicate with the researchers from different countries of all over the world, and I'm really happy to have this communication this evening. Thank you very much. Thank you everybody.
Okay, thank you, Oleg, for this webinar, for this for your topic, for your sharing experience, and for your discussions, for answering the questions. And thanks to everyone who attended the webinar. Please don't forget about our Facebook page. Look for this and previous videos of our webinars on official YouTube channel. Subscribe it, like it, follow us, and don't forget about the next Young Members Group International events. We will have something new and interesting this year. So follow us, and I wish to everyone be healthy and active. And see you in the next Young Members Group webinars or other actions. So it will be even cooler. So thank you and goodbye to everyone.
Goodbye.